What do you say to a programmer on their birthday? Many happy returns. Today's talk is about many happy returns and maybe some not so happy ones as well. So what are we going to talk about? Specifically, these two features. The first one is the trailing return type up here in that little arrow int. And the other is just leaving off the return type entirely and just letting the function deduce the return type for you. A little bit about me. I've been talking here since the very beginning, the first conference in 2014. 8th year presenting, ninth talk total. I live in Boston, and I'm an independent software developer. I've been a member of the C++ Standards Committee since like 2007 or something like that. And importantly, I'm one of the contributors to the book, Embracing Modern C++ Safely, which is this book, which is out now. This book is about C++ 11 and C++ 14 with some references to 17 and 20 as well. And it's broken up into 3 big chapters. Safe features. These are things you can just use. They're easy to use. They're hard to misuse. Conditionally safe features. They are easy to use correctly, but also subject to some misuse. And then unsafe features. These are the ones that are hard to use correctly, easy to use incorrectly. They all have a place in the world, including the unsafe features. It's just that when you get to the harder, the less safe features, you want to be extra careful and avoid using them when you don't need them. Each chapter is divided into features, and each feature is divided into these 4 sections. The description, use cases, like what would you use this feature for? Potential pitfalls, where can you get in trouble? And annoyances, things that don't necessarily get you in trouble, but make it a little harder to use than you would hope. This talk follows that format. We're talking about 2 features that are in the book, and I follow this format for each of the features. So let's get started with trailing return types. So this is a trailing return type. Instead of putting the return type int at the beginning of the line, at the beginning of the declaration of a function, I put it at the end after the arrow. If we have attributes or exceptions, the attributes go in the normal place. The exceptions go also in the normal place, but before the return type. Templates are really no different. You have got, instead of putting the return type at the beginning, you put it at the end. There are situations where templates are easier to write with the trailing return type, and we'll get to that. These 2 formats, these 2 syntaxes are exactly equivalent. You can actually declare a function using one of the syntaxes and define it using the other syntax, and the compiler will be fine with that. So we looked at sort of namespace scope functions. Let's look at member functions. It's the same idea, but you have to know where to put all the various declarations. So, for example, the CV qualifiers and reference qualifiers for your function, that is the this pointer, they go before the return type. So if it's a function that can be called only on const objects, that const goes before the return type. If it's a function that can be called only for R-value references, as the second to last one C is, that amper goes before the return type. But the declarations override and final, they go at the end, after the return type. So if you get started with this and you start using these declarations, you're going to get it wrong. That's okay, the compiler will tell you, you'll fix it, you'll get used to it. Now, here's some situations where things get easier when you're using a trailing return type. So here we have a namespace NS. Inside that namespace, we have a class template C. We also have a struct S. And inside that struct S, we have a type E. So to refer to E, you have to say ns : s : E, right? That's all the scoping. But inside the class itself, you don't need to say any of that, right? If you look at the declaration here, the trailing return type, and this would be the same if it were a leading return type, is simply C of E. You don't have to repeat the namespace, you don't have to repeat the class name. But in a separate definition, down here, ooh, that return type is ugly, right? If you look on the right-hand side, you see the return type. With the trailing return type, you don't have to specify that namespace again. You don't have to specify the class name again, the class scope again. You just use it the same way you did inside the class specification itself. So that's a nice little, easier to read syntax. The more important benefit you get from here is the ability to refer to one of your arguments by name. And this is always in the context of a decal type, and we'll look at that in a second. So look at the first example is doing it the hard way. We're returning an iterator to the middle of this vector, and we have to specify that return type. That first return type is pretty hard to type out, right? You have to type out std vector int const iterator. It's really easy to forget that it's a const iterator, but it is, and so you have to put that const in. We'll wait for the video to come back. Okay. The second one is actually more verbose. This is with a leading return type still. It's actually more verbose, but a little less prone to error. Well, that's debatable whether or not it's less error prone. Here we're saying the type that begin returns. That's what we want. Okay, so we're using Decotype. But look at that middle thing, that decal val. What is that? Oops, I'm using the wrong button. That decal val right there. What that is a standard library function. I don't know how many people have used decal val? So about half of you, maybe less. It is really a meta-programming technique. Decal val is a function in the standard library that returns an R-value reference, or a collapsed reference, really, to the type that's in the angle brackets. But it doesn't actually return it, because it has no body. It's only for use in unevaluated contexts like size of or decal val. And so here, we say, well, we want a vector, and we want to call begin on it, but we don't have the name, we don't actually have a variable of vector type, so we call decal val that synthesizes one out of thin air. Now, we can't actually call this at runtime, but we can put that inside of a decal type, and it'll tell us the type of the thing that begin returns. Still pretty complicated. Now look at the last example. This is where you really see the benefit of the trailing return type with decal type. We say, give me the type of v.begin. That's the iterator type, right? That's what we want. Very easy to write, very easy to understand, and very likely to be correct. So this talk is not about decal type, but there's some things you really better understand about it as we go on. One of the things is that decal type, you say decal type and you pass it an expression, and it preserves everything about the type of that expression, including whether it's a reference and whether it's a const or volatile qualified. And if the expression is an L value, meaning something you can modify, or you can assign to, you can take the address of. Really, with an L value, you can think of as something you can take the address of. Then it shows up as a reference. Okay, there's a special case that I'll get to in a second, which is if the expression is actually an ID expression. I'll get to that in a minute. So sometimes you want to discard these qualifiers. Sometimes you don't want a reference returned. So in this first function, the first example, the f returns a reference to the thing that p points to. Okay, so a reference to the integer. Okay, suppose we don't want that. Then the best thing to do is to use this remove cvref t and then we get just the int. Now, some people are still not using C++20 compilers. So earlier versions, you can use remove reference T, and then there's a separate step you can use to remove CV qualifiers if you care. Often, since it's the return type and it's a top-level type, those CV qualifiers are kind of thrown away by automatically anyway. So you don't usually have to worry about the difference between these two. So here's the special case I was getting to. If the thing inside Decotype is an ID expression, that's the technical term, which basically means like a variable name, a function name, something like that, then what gets returned is the type that thing was declared as, and it doesn't preserve whether it's an L value or not. It doesn't make it a reference. But if you put an extra pair of parentheses around that, it's no longer an ID expression. Now it's a regular expression. And it says, oh, it's an L value, so I'm going to make it a reference. So that's my quick introduction to Decotype for those who have not seen it before, and even for those of you who have seen it before and didn't know these subtleties. It's a little subtle. It usually gives you what you want, but sometimes you can really get it wrong. So regardless of the specific subtleties about Decotype, you have to just think carefully. Do I want to preserve references or not? And then go from there. Okay, now that we have the syntax, we're trying a different dongle for the video. Let's hope for the best. Now that we have the syntax, let's talk about the use cases. Why do we want to use trailing return types? So some of them we've seen already. The simplification where you can use the name of one of the arguments in your, it's still figuring itself out. Thought it had it. There we go. In addition, it's generally a simpler way to express complex return types. Here's a function f that returns a pointer to function, and a function g that returns a pointer to member function. In the leading return type case on the left, you'll see that the return type is kind of split between the front and the back of the actual function signature. But with the trailing return type, it's all together, nice and, expressible. And then a lot of times, how many times have you seen code where there's a type def just for the function return type because you can't actually, your brain just won't figure out how to do it right and the other way. This makes it less likely that you'll need that spurious type def. Not that the type def's a bad idea, but you don't always need it. Here's another complex return type. Here's a function template that's returning a type that's dependent on one of the template arguments. Now here you can get into some pretty complicated metaprogramming sometimes. Here we're just using Decotype here, but this is the example, similar to the example I showed before, where we had to use this decal val, wrong button, decal val, to get the arguments to the thing we're computing instead of using Decotype. Notice that we're computing the Decotype instead of just specifying the return type because you may not know what the sum of the two arguments might be, what the type might be. We have two template arguments. They might be, one might be an iterator and the other might be an integer, and the result is an iterator. Or they might be both numeric, and the result is the common type between them. One might be long, the other one int, and so on. So we use Decotype to figure it out rather than trying to figure it out through some other voodoo. In the case of the trailing return type on the right, you see that we can just say this is the expression we want, whose type we want. Now, something to pay attention to here is that we see the same expression twice in the return type and also in the function return. We'll get back to that. Why do we need to say it twice? Sometimes we don't. Okay, lambda expressions. Lambda expressions can't use the leading return type syntax. This is the only way you can specify the return type for a lambda expression. Well, except for the automatic deduced method, which we'll see. But if you want to specify the return type for a lambda expression, you have to use the trailing return type syntax. So the key points to remember about trailing return types is a chapter 1 feature. Use it without worrying. It's unlikely you're going to do something worse than you would do with the leading return type, right? It's a safe feature, which is why I didn't do pitfalls and annoyances, because there aren't any significant ones to speak of. It simplifies the expression of complex return types. It separates the return type from the function signature, makes it easier to read in many cases. You get consistency with lambdas. And like I said, no significant pitfalls or annoyances. Now we move into auto return. This is where the magic comes in. It's also where the pitfalls come in. Now that we all are experts in trailing return types, I'm going to be using them consistently through most of the slides from here on in. So the thing on the left, instead of being leading return types, is now the thing we already know, the trailing return type. So on the left, we have a defined return type, which is really what I'm contrasting here. Defined return type versus automatically deduced return type. In the left, we have the defined return type. We define the return as being of type int. On the right, we leave the return type out entirely. Right? We have this auto in the front, which we have in both cases with leading return types. I think I kind of glossed over that before. In the leading return type, in the trailing return type, where the leading return type would be, you have the word auto. Don't forget that. And believe me, I forget it all the time. Well, not so much anymore, but when I first started using trailing return types, I forgot to put that auto in the front. So both of them have an auto in the front. But the one on the right doesn't have the arrow with the return type. So what's the return type? The return type is deduced from the return statement. The expression that is being returned is what you get. Here's an example using a template. And on the right, I'm using an alternative syntax, which is kind of a hybrid between the auto return type and the trailing return type, which is the trailing placeholder. Okay? This is a trailing placeholder. The auto placeholder, it shows up both on the left to introduce the thing and says this has an auto return, and on the right saying this is auto rather than defined return type. Okay, but it has the same meaning as just leaving it off entirely. I'll explain why you might want to use this a little bit later, but right now, just know that it's a different way of saying the same thing. Arrow auto is the same thing as just leaving it off. Okay, so now this was the example we saw before, where we have a plus b divided by 2, and we want to know its type. Now we don't have to say it twice. It's deduced for us. So like I said, it's deduced from the return expression. And when there's no return expression, it's deduced as void. So there's two ways for that to happen. Either there's no return statement at all in the function, in which case it returns void, or there is a return statement, but that doesn't have an expression after it. What happens when there's multiple return statements? They have to yield exactly the same deduced type, otherwise it's a compilation error. So in our first example here, we have two return expressions, I minus 1 divided by 2, or I divided by 2. Both of them are integer expressions. If you do this computation with integers, nothing causes it to change to long or unsigned or something like that. So that's good. So there's no problem here. Both return branches, both branches of the if statement return the same type. But here's an example where it looks innocent enough, but isn't quite right. We're returning, for the first return statement, we're returning x, which is of type long, and the second one we're returning 0, which is a literal integer. And because they don't match, the compiler is going to complain. So we could just put an L on the 0, but if this was a template, that would probably be the wrong idea, right? We don't necessarily know that that we need along here. So instead, this is one situation where you might want to use the question mark colon ternary operator, because it figures out that, hey, int and long have this common type. And so that's what we'll return. This is a pretty common technique. It doesn't solve all your problems, but it's a pretty common technique. I'm going to digress for a moment and talk about the bigger topic of auto, which is, we start with template parameter type deduction, which is where most of the rules come from. So we're not using auto at this point here. We just have 3 templates, 3 function templates. The first one just takes a t argument, the second a t reference, and the third a t pointer. When the function is instantiated, there's a pattern matching that goes on to figure out what is actually t and what is the actual type of v. So if we have a constant integer, a variable of type const int called c, and we pass it to each of these cases, in the first case, we say, oh, okay, well, c is an int, right? The const qualifier disappears because it's passed by value. And so c is int. In the second case, its L value-ness is preserved. The fact that that you can take its address is preserved because we're matching with a reference. So now, also the const qualifier has to also be preserved when you're doing that. So that's the match there. This, I hope, is not new to most of you. In the third case, if we take the address of c, we get a pointer to const int, and it matches that, right? But if we were to pass c into that last template without taking its address, we get an error. We can't form a pointer from an integer. And because of that, this pattern matching gives us a couple of benefits. First of all, we can extract t. You know, we say t is an int in the case in the third call, the second to last call. But also, we prevent accidentally calling a function with something like, I really want a pointer. So this is a very simple form of sort of constraining your template. The same thing with the second one, with G, says we can't pass this, what is called a PR value, like the return value of a function that doesn't return a reference. You can't pass that into G. The pattern match will fail. You can't take a reference to something that is like a temporary variable. You can get a const reference to it, but that's a special case. Now, in C++11, we kind of extended this notion, not just to template arguments, but to variables that you can declare using auto. And the same rules apply. So again, we have our const int c, and the first line, the c2, is just an int, whereas c3 is a constant ref, same pattern match as the template argument. And we take the address of c and assign it to this auto using auto star, we get a constant pointer. All right, and then the last one again fails for the same reason that we did before. So this pattern match, where you're putting decorations like ampersands and const qualifiers and so on your auto, lets you do this pattern match. And sometimes the pattern match is to say, prefer this over that, in the case of the template arguments. And sometimes it's to prevent something from happening. But just know that it works the same way as the template arguments. Now back to auto return. The auto placeholder on the left can be decorated the same way as a template argument, template parameter, or an auto variable, right? With reference and const qualifiers and so on. And all of the same pattern matching. I'm not going to go one by one through all of these. You can kind of glance at them and you can look at the slides later after the conference is over. But the things to look at, for example, is the The declaration of F6 deduces a reference to function returning C. That's kind of cool, right? And then the last two, the error cases, again, you cannot deduce the pointer from C. C is an object of class C. It is not a pointer type. And then the last one is actually one of, it's kind of between a pitfall and an annoyance. It would be a pitfall in that you're returning a reference to a local variable, and that's bad, a temporary variable in this case, and that's bad. I demote it a little bit to an annoyance because every compiler diagnoses this, at least in this simple case. But I suppose there might be more complicated cases where you can get it wrong. I suppose that, for example, if you take a reference to something inside of your function and then you return that reference, it may have lost the thread that this reference was originally bound to a local variable or something like that. I haven't tested that, how smart the compilers are about that. So don't do that. Just like any other situation, you don't return a reference to a local variable or a temporary variable. Conversion operators. This one, when I was studying this subject, was the most surprising thing I'd ever seen. You can actually have a conversion operator where the thing it converts to is deduced from the return statement in the operator, okay? The rules are really the same. It's just seems a little weird to me. Like, I don't know what I'm converting to, so here. And I suppose the use cases are pretty much the same. All of the previous things apply, but one of the things to be concerned at is because you have the name of the operator is in a sense not known until you deduce its return type, the overloading rules are a little bit funny. And you look at the first two declarations of auto, they return different types. So they theoretically have different names. One of them should be named operator int, operator int, and the other one should be called operator double. But because we called them auto, the compiler says they have the same name, they have exactly the same prototype. Therefore, I can't tell them apart. And the second one is a redeclaration of the first. And you're not allowed to do that. And the reason why that happens, by the way, and this will come up again and later on in the discussion, is that compilation happens in phases. And actually interpreting the body of a function happens later than interpreting its prototype and its signature. So, but by the time we know its return type, it's too late. We have long ago said, these things are in conflict. Oh, I should mention that the reason that the other two work fine is because something is different about their actual signatures. Right? The third one is for R-value references only, like operating on a temporary, for example. And the last one has the pattern match on auto star, so it only returns pointers. And therefore, it's a different signature than the others. There are syntactic limitations as well to the use of these deduced return types. First of all, the declaration and the definition have to match, or any redeclarations, they have to match. So either it's deduced or it's not deduced, but you can't change your mind in the middle. Right? So in this example here, we changed our mind. We say, it's deduced. No, actually, it's actually int. No, you can't do that. There are a couple of situations that it's just disallowed. You're not allowed to use it on virtual functions. You're not allowed to deduce an initializer list. And the reason why you can't deduce an initializer list is because an initializer list has, it's basically like a temporary. And if it got returned, the initializer list would be out of scope before you could actually use it. And it doesn't deduce. I know you could save vector of t in a template argument, but you can't use it here. It won't do the pattern match on that. You also can't figure out the type of a function until the body has been seen, because you don't know the return type. So we know that f takes a double argument, but we don't know what type it returns until we see the second definition. And if we take the address of f, we don't know what type that pointer is. It's a pointer to some function that takes double, but we don't know what that returns. The second address of works fine because we already know the type. Common sense for the most part. I'm going to mention Decotype Auto, which is a little bit more of an advanced feature, and it was introduced in C++ 14. Decotype Auto solves some problems that Auto caused, if you will. And what it does is that when you deduce something using Decotype Auto, it preserves the value category of the thing it's deducing. So that means if it's a reference, you preserve the fact that it's a reference. A little bit like the Decotype operator preserves the value category of the thing, the expression that it was given. So our first example, we have a function called g that returns a float by reference, by const reference. If we just call g and we assign the variable using auto, we get a float. We throw away the fact that it's a reference, and because it's a top-level thing, we throw away the const as well. But if we declare f2 to be Decotype Auto, it preserves the fact that the thing on the right of the equal is a reference. And the same is true for move. So move, it returns an R value reference, but we throw that away with auto. We preserve it with Decotype Auto. So the same rule applies for the deduced return type. If we just say auto, which is usually what we do, then the reference qualifiers and top-level CV qualifiers are discarded. But if we use Decotype Auto, they are preserved. And there's a very specific use case for that second case, for the Decotype Auto case. So that's a quick introduction to Decotype Auto. Another thing to know about Decotype Auto is that you can't decorate it. And this is true both for variables and for the return types. You can't put ampersands and stuff around it. You can use the trailing placeholder syntax if you want. So you could say arrow Decotype Auto. So auto at the beginning, and then arrow Decotype Auto. And that's useful, especially useful for lambda expressions, because there's no place to put the Decotype Auto otherwise, right? And this is, by the way, G is returning from the previous slide, G is returning a reference. And if we want this lambda expression to return a reference, we actually have very little choice but to put something like arrow Decotype Auto here. We have to put something there. So why do we want this? I'm sure you've already thought of several situations, several nice conveniences that it gives you, right? The complex return types comes back again, but even more so. I'm going to give a nice little full example. In the book, this example is fleshed out even better. So I'm going to have to go through this kind of quickly. We're going to create kind of a unit library. And by the way, there are proposals to make something like this standard, but they're much more sophisticated. This is a kind of a dumbed down version, if you will. But it's not too dumbed down. It's got some nice things about it. A unit is something that it expresses a unit in the MKS, meaning meters, kilograms, seconds, unit system. And any unit in the MKS system, there's an exponent for each of those, distance, mass, and time, that says, like, what's the dimension? So for example, if you look at using the type defs down below, you'll see that square meters is a unit that has an exponent of 2 for distance because it's square meters, and exponents of 0 for the other units. It doesn't have any time component or mass component to it. Does that make sense? And whereas meters, for example, has a 1 for the distance component, and kilograms has a 1 for the mass component, and 0 for the others. Speed, in like meters per second, has a 1 for the distance and a -1 because it's in the denominator for the time component, right? So it's the unit of speed is meters per second, right? This is kind of, high school physics stuff. I'm sure some of you have blocked it out, so there's a quick reminder. When you divide units, you divide unit-full quantities, you subtract the exponents. You subtract the exponents from the second unit from the exponents of the first unit. We'll see how that works in a second. But the resulting unit is arrived at by, as you can see, we take our distance, we take the difference between the distance exponents. Remember, these are not how far, but what dimensionality of how far. Is it meters? Is it square meters? Is it cubic meters? That kind of thing. So we compute d, m, and t by taking the difference of the corresponding, from the corresponding units. And then we return a unit that has those 3 exponents. We simply get the quotient of the 2 values, and that's what we return. That is a deduced return type. So we didn't have to say that twice. We only said it once. So that's nice. And we test it out. We get a meter's distance of 100 meters, 2 seconds, and we divide 100 meters by 2 seconds, and we get 50 meters per second. Meters per second, we have subtracted, we have the negative seconds now on the exponent, and a positive 1 in the meters part. So this is pretty cool, and unit libraries take advantage of this auto return. We could express this fully, but it would become a little messy, a little harder to read, right? I kind of like the fact that I can compute each of the 3 parts using these const expr expressions and then put them together at the end instead of writing them all out into this long return type. Another use case is just let the compiler apply the rules. We have this thing, this function I call half interval, which is give me something halfway between v1 and v2. I'm sorry, not halfway between, but tell me what the halfway, how far from v1 is the midpoint to v2. So we subtract them, divide by 2. But again, what types are involved here? Well, this is nice auto return, so it just figures it out for me. If I pass it, for example, a long and an int, it says, oh, well, the result has to be a long. If I pass it 2 iterators, it says, oh, well, the result has to be a difference type. It doesn't figure out that the result is a difference type. It just figures out what the result is and says, what's that type? If we wanted to spell that out, it would be that long thing on the bottom right. The alternative to letting the compiler do it in the return statement is to do it twice. Do it using Decotype in the return type, with the defined return type, and also doing it in the return expression. Is that bad? Not always. Sometimes that's actually the right answer. So you don't always have to reach for this, but I'm getting ahead of myself. The only way to return a lambda closure is with auto return type. So here we have a function called addN. What addN does is it takes a function n and it returns a function that takes another value, v, and adds n to it. Okay? It's a function that takes 1 argument, returns another function that takes 1 argument. And the result is a sum, something that takes 2 arguments. So this is somewhere, depending on exactly how you think of it, in functional programming, this is partial application You can think of it as currying. This is not technically currying exactly, but it is similar to that. But it is a partial application. So we partially apply the sum operation, and we return something that's callable. And that's really useful in our transform down below. We're going to take our vector, we're going to transform every element by subtracting 4 from it. That thing on the end there. And this thing, okay. So in order to make this work, our add-n function has to return a lambda. It has to return a lambda closure. What happens if we try to do it the other way? Well, a lambda has a unique type. 2 identical lambdas have separate unique types. They are not the same type. So they look the same, but they're not the same. Therefore, this would not compile, the thing on the bottom. Another use case. Perfect function return forwarding. Suppose we want to call a function, but we want to do something before we call it, maybe do something after we call it, or both. In this case, what we want to do is we want to grab a mutex lock before we call the function, and then release the lock when we're done. Well, when we do that, we want to make sure that we get exactly the same result we would get if we just called the function directly. You know, just because we're grabbing a mutex lock doesn't change the return type, same as if we were logging or something like that. So this is it's a function wrapper, or a function that wraps another function. And all this forwarding stuff is a little messy, but it's what you have to do. It says, let's forward all the arguments into the function exactly as they were specified on the call line. And the function that was passed in, we have to forward that in exactly as it was passed in. So we put a forward on that. And then we return the result. When we return the result, the function thread-safe invoke deduces the correct return type. And notice we're using Decotype Auto, so if the thing returns a reference, we get a reference. I'll let you stare at that for just a second. If you're not familiar with mutex locks, I mean, or lock guard. It's basically a type that says, lock the mutex when we construct this thing and unlock it when this thing goes out of scope. So we don't have to remember to unlock it. It's safe to return. It's safe to throw an exception. The thing will get unlocked. So this is actually very cool, I think. And you know, it kind of completes the picture of perfect forwarding. But all this power comes with great responsibility. So let's look at some of the pitfalls. The biggest pitfall is probably that you lose abstraction and insulation. So abstraction, a function is abstract if it can be understood independent of its implementation. Well, the return type isn't even in the function prototype anymore. So the function can't really be fully understood without looking at the implementation. And okay. The other thing I'm talking about is insulation. So the first is abstraction. Insulation is the ability to make a change to a function and not recompile the world. So inline functions, you could say, well, inline functions already break insulation, right? Yes and no. Yes, they do, in that if you change the body of an inline function, you have to recompile anything that used it. But you could change your mind, take the inline off, move that inline function into a CPP file in a separate compilation unit, and everything will have the same meaning. It might be less efficient. It might not be less efficient, depending on your optimizer and your LTO, but you can do that. It's a little harder to do that with a deduced return type, because now you have to change your deduced return type into a defined return type. You can't just move the body of the function into a separate compilation unit. And loss of clarity. It's just harder to read these things sometimes. You just don't know what's going on. The implementation, it makes it harder for the user to figure out what's going on. The compiler can figure it out easy. The user may not have such an easy time. And if there's recursion or calling other functions, this gets even more complicated. So what can we do about this? Suppose we really want to use a deduced return type for one of the benefits that we mentioned in all of the use cases. Well, if possible, use a defined return type. That obviously, the pitfalls of a deduced return type don't apply if you don't deduce the return type. Keep the function short and simple so that it is readable to the human. Document, document, document. All right? Documentation can solve a lot of problems that obscure code produces. Some people say, there's this thing about comments are a code smell, not when you are documenting the interface of a function. Lack of comments is a code smell if you have a public function and you are not documenting it. Describe the qualities of the return type in your documentation. So for example, the return value is a pointer-like object that supports postfix operator ++. That is actually a very powerful statement. The reader can really understand what's coming back, even if they don't know its type. And maybe they'll never know its type because it's a complex, weird type, And that's okay, because what they know is how to use it. And in fact, when you do this, you're actually raising the level of abstractions. You may be actually creating something that is even more abstract than if you had used the defined return type and relied on that to communicate something, right? So even if you are using a defined return type, you may want to say, this return type, which may be this long, what it is a pointer-like object that can be post-incremented. Another pitfall, refactoring errors. These two don't have the same meaning. Can anybody tell me why? Tricky, huh? What does the first one return? What's the type of that first return? Looking at that last call at the bottom, the call to mid at the bottom, where we're passing the two iterators in. Yeah?
I think it's the right-hand one returns a ref, the second one does not.
It's actually the other way. Oh. The left one returns a ref because it's using Decotype operator. Okay? So it's dereferencing the iterator that we produce with that interesting formula. And the dereference iterator, because it's a vector iterator, or most container iterators have this quality, when you dereference it, you get a reference. And we're preserving that reference here because we're using Decotype. The one on the right is just using auto, and it discards the reference qualification. Subtle. So this is a pitfall to watch out for. It's not really a flaw in either feature. It's kind of just the way Decotype operator works that you just have to understand. I kind of strained at this for a little bit, thinking, which feature was done incorrectly? And I can't say that either one, or even Decotype itself. Decotype, actually, I have some qualms with. Decotype, I think, should have been two separate operators, one that preserves and one that doesn't preserve the reference stuff. Oh well. So this is what I just said, that if you use a defined return type that uses the Decotype operator, you're going to preserve the value category of the return, whereas a deduced return type, unless you use Decotype Auto, will discard it. So how do you mitigate this particular problem? Well, again, you have to pay attention to what you're trying to do. Am I trying to return a possible reference or not? Then figure out what the mitigation strategy is. If you're using a deduced return type and you want to preserve the value category, then use Decotype Auto. If you want to always return a reference, use auto-ref or auto-ref-ref, depending on what you want to return. Right? You decorate that. Conversely, and of course what I left out was the third case, which is if you don't want to preserve it, then just use regular auto. Conversely, if you're using a defined return type with the Decotype operator and you don't want to preserve the value category, then you use one of the remove reference T or remove CVRef T, as I mentioned earlier. But the first point is the most important one. In any of these cases, pay attention to what you want. Do you want to preserve the value category? Do I want to always make it a reference, never make it a reference, or follow the actual expression? And then learn the correct rules for doing that. Recursion. There's a sensitivity in the return order. Suppose we're computing recursive factorial. If n is less than 1, we return 1. Otherwise, we recurse, right? That's okay. The first return says we're going to deduce int, and the second one says, oh, we've already deduced that this is int, so we're good. If we reverse the order and do the recursive call first, we say, hey, you're calling a function whose return type we don't know yet. And then when we actually do deduce the correct return type, it's too late. We've already seen the error. Chances that you'll make this mistake, very slim, unless you write your recursions backward from the rest of the world. Everybody else, I've always put the base case first, right? Same is true for compile time recursion. This may look very similar to what I did before, but it's not. We actually have two different templates. The first one is when we have exactly one argument, and it simply returns V. And it's auto-deducing based on the type of V. And the second one is for more than one argument, and it makes the recursive call, but it's not really a recursive call. It's a call to a recursively defined template, a different function. Each one of these sums has one call to sum has one fewer argument. So it's a different template instantiation. But the principle is the same. The first specialization has to, the first overload has to be seen before the second one is parsed. Otherwise, you get the error that it doesn't know the return type. Or you might get an infinite recursion. I'm not sure in this case. No, you get that it can't deduce it. Okay. Another annoyance. No spine on the return type. Here we have I'm going to go through this quickly because it's really kind of a semi-advanced technique. But if you deduce a return type using a defined return type, if you use Decotype to figure out the return type, it will discard any overloads that just can't be formed because of a substitution failure. So when we call print and we pass it a struct s, it says, okay, the first overload works fine because v.print is a valid expression. The second overload also works fine because void is obviously a valid return type. But the first one is preferred because we're passing an int instead of trying to match the ellipsis, the ellipsis symbol. Okay, but if I would make the same call and I would pass hello, which is what? An array of char. The first one fails deduction. So it gets removed from the overload set. And then the second one is the only one left. And so that's what gets called. You get the fallback of just using streaming. So this is nice and this is cool. But this is with defined return types. Hey, wait. That first one, that first declaration, I'm repeating v.print in the prototype and in the body. That seems redundant. Why don't I use auto return instead? Well, this is why. Because no longer do we have a substitution failure in defining the return type. So the first call works fine again, because both are valid functions. But the second one, instead of removing something from the overload set, it matches it. It says, this is the preferred overload. And then it tries to parse the body and says, oh, I can't do that. And you get a hard error instead of something being removed from the overload set. Okay, so that's an annoyance, something you can't do using deduced return types. And so, wrapping up here, this is a chapter 3 feature in the book. Use it with caution. Okay, When you use it correctly, it can actually make your code easier to read and simpler. Use it wrong, and you can obfuscate things, you can cause maintenance headaches. Note the difference between Decotype Auto and regular auto, all those reference things, and preserving. Just because something shows up twice doesn't mean you should change from the defined return type to deduced return type. So when in doubt, do without. Okay, I have a minute for questions and I'll stay. Thank you.
Few slides ago, I did not understand what that int was for. There's an int.
There's an int at the end.
It's not
and that
used.
is to say that this overload is better than that overload. So int is a better match for 0 than ...
Okay.
Okay, so it's a trick that, and that's why there's this indirection. Print calls print imp, and the print imp has the two, so it's a way of ordering the overloads to say this one's preferred, all else being equal, this one's preferred.
Okay.
Hey, so we marked this as an unsafe feature in the book, right? I was wondering, now that we have C++20 concepts, what are your thoughts on actually constraining the deduced return type? Do you feel like using a concept in conjunction with deduced return types could make this a safer feature? What are your thoughts on that? I'm curious.
I think, yes, I do think it would be a safer feature used with constrained templates. Certainly some of the spina stuff would go away, that annoyance. You could use constraints to get around that. And the issue of other kinds of hard errors you might resolve. So I think it would make it easier. I think the pitfalls are still there. I just haven't fully analyzed that, but it did occur to me that concepts would make this a bit of a safer feature.
Oh, back on from online. Back on slide 22. I don't know if you want to bring that up, but the question refers to slide 22.
Slide 22. Where's my slide number? 22?
Yes, 22.
I go way back. Oh gosh. Okay. Here we go.
Okay. The question: can I get the type of the templated argument and then construct an object with that type to return in the else statement?
Say that again.
Maybe it's not. Can I get the type of the templated argument and then construct an object with that type to return in the else statement? It might be a different slide.
When you presented this, can I maybe use the mic?
Thank you.
So when you presented this, you hypothetically mentioned that the second case with the if else might not work well instead of long if you have a template parameter, right?
Right.
And you said to use the ternary, and the question is, would you be able to do that? And you could use the decal type thing, right?
Yes, right. Yes. If you had a template parameter of type T, you might want to cast the 0 to T. If that seems like a reasonable thing to do, then yes, that is a different way of solving the same problem. Or what I would normally do in a situation like that is return T open close curly brace, because maybe it's not numeric, and I want it to just return a default constructed T. Yeah.
I have two questions about Decotype Auto. First of all, are there cases in which Decotype Auto and Auto ampersand will generate different outcomes? Mm-hmm. And secondly, in the last example you showed us, is there any way or cases in which Decotype Auto could be used in a sphere-friendly manner to avoid the DRI violation, duplicate code?
All right, let me answer the first one first. This is the situation This is like the poster child situation where Decotype Auto returns a different result than auto ref. If the function returns an R value, say an int, then Decotype Auto deduces int instead of int ref. Int ref would not work here because it would be a reference to a temporary. So you couldn't use auto ref here. It would not give you the right result.
Okay.
It has to remember, it says, in this case, I absolutely have to return a copy.
It would compile like would be dangling reference, right?
That's right, it would be a dangling reference, and the compiler's accessed, I'll warn you about it. And the second question was?
Decotype Auto as a way of avoiding DRI violations in a SFINA friendly manner.
Decotype Auto.
Avoiding the need to use to return a decal type of an expression you to duplicate.
I don't see how, but let's talk after because my time is over. But I'd like to understand your question a little bit better and answer. So thank you very much. My time is over. I'll stay a little bit.